Microcontrollers. A microcontroller is an integrated circuit designed to control tasks in an embedded system. Usually, a microcontroller contains a processor, memory, and input-output I/O peripherals. And yes, this is all on a single chip. A microcontroller is the main component on an embedded system. However, an embedded system includes the microcontroller and surrounding hardware components. In industry, the embedded system is often contained in machinery and manufacturing equipment. A microcontroller is sometimes called an MCU. They are found in cars, robots, photocopiers, coffee makers, medical equipment, radios, and appliances like refrigerators. The list goes on. They are basically mini personal computers designed for control without a complex operating system. How do microcontrollers work? Generally, an MCU receives and outputs data through I/O peripherals, or pins. A central processor stores this working information in data memory. Controlled by a computer programming language, the processor performs arithmetic operations. The computer programming determines how the MCU performs its tasks. A complex embedded system may use several MCUs. An automobile is an example. A car may have different systems, for example, anti-lock braking system, fuel injection, or emissions control. MCUs may need to communicate with each other or a central computer system. Again, I/O peripherals are used to receive and send data. What are the components of a microcontroller? The core components of a microcontroller are the processor, CPU. It processes and reacts to different instructions to direct the microcontroller's task. This includes arithmetic, logic, and I/O operations. It also facilitates data transfer, which communicates with the larger embedded system. Memory. Memory stores data that the processor receives, and the MCU responds with instruction it has been programmed to perform. A microcontroller has two main types of memory. Program memory. This is long-term storage of data. It relates to the instructions that the CPU performs. Program memory is non-volatile memory. This means it holds information even when the power is disconnected. Data memory. This is temporary storage of data. Data memory is used when instructions are being executed. Data memory is volatile. This means data is lost when the power is disconnected. I/O peripherals. The input and output peripherals is how the processor communicates to the external environment. Input ports receive data and send it to the processor via binary data. The processor receives that data and sends necessary instructions to output devices. These are devices external to the microcontroller. Core components of an MCU. The processor, memory, and I/O peripherals are the core components of a microprocessor. However, other components include ADCs, or analog to digital converters. An ADC is a circuit that converts analog signals to digital signals. This is useful for interacting and interfacing the processor with external analog devices like sensors. Next, digital to analog converter, a DAC. A DAC, or a DAC, does the opposite of an ADC. It helps the processor interface its outgoing digital signals to external analog components. System bus. The system bus is the pathway that connects all components of the MCU together. Serial port. One example of an I/O port is the serial port. It allows the MCU to connect externally. On hobby MCUs, it is the USB or parallel port. However, it can differ in the way it exchanges bits. Varying features of MCUs. Depending on the application, an MCU's processor may vary. They range from 4, 8, 16, 32, or 64-bit processors. The latter are more complex. MCUs may use volatile memory, like random access memory, RAM. MCUs may use non-volatile memory, like flash, EEPROM, and EEPROM. Mostly, MCUs are designed to be readily usable, requiring no additional computing. They are self-sufficient, meaning sufficient onboard memory and sufficient enough I/O peripherals. Generally, MCU architecture is either Harvard or von Neumann. This means each offer different methods of data exchange between the processor and memory. With Harvard architecture, the data bus and instructions are separate, permitting simultaneous data transfer. With von Neumann, both data and instructions use one bus. MCU processors can be based on differing computational instruction sets, complex or reduced, as in CISC and RISC. In general, CISC has about 80 instructions, while RISC has 30. Also, CISC has more addressing modes, 12 to 24, compared to RISC, 3 to 5. While CISC can be easier and uses memory more efficiently, performance can be worse due to increased clock cycles required to execute instructions. RISC, which emphasizes software, often provides better performance. CISC processors have more hardware emphasis because of its simplified instruction set. Conversely, RISC's software can also be more complex. The instruction set is determined by the application. When first introduced, MCUs used assembly language. Nowadays, C programming is more popular. Python and Java are also popular. As mentioned, MCUs feature I/O peripherals, or pins. Popular uses include ADCs, LCD screen controllers, real-time clocks, RTCs, USART and UART, and the Universal Serial Bus, or USB connectivity. Also available are a plethora of sensors for collecting data like humidity and temperature. Historically, the first parts of the microchip PIC family were available in 1976. The Intel MCS51, referred to as an 8051 microcontroller, was first developed in 1985. The AVR microcontroller was developed by Atmel in 1996. Well, thank you very much for listening. I am not an expert, and what you just heard was developed and written by me. If you like what you heard and you want to learn along with me, please consider subscribing to my channel. I'm into hobby electronics, microcontrollers, and to some extent radio and a few other things. So thank you very much for listening. Once again, I am not an expert, but I am a genuine enthusiast. Thanks for listening.